pressure is something that is easy enough to calculate. You just plug numbers into an equation. But to have an understanding of what the difference between pressure and force is, maybe a little more challenging. Let's test you out here. Let's say we have a thumbtack here, and two people come toward each other and they push the thumbtack. And my question is, which person would receive a greater amount of force? And let's see if you saw that. Let me just play that one time again, but look very carefully at that thumbtack. Oh, did you see it? It did not accelerate. So Newton's second law says no acceleration, there's no net force. So the hand A pushing on that has to equal thumb B pushing on that. And so because it didn't accelerate, the two forces must have been equal. So they receive the same amount of force. If you kind of went with your gut instinct on that and said, ooh, that's going to hurt, you might be tempted to say that A had more force, but it didn't. The question now is, which person experiences a greater pressure? And that would be A, because the force that is applied to A is over a much smaller area. And if I had these two identical books, and the question is, which one puts more force on the table? Well, if they weigh 5 pounds each, they both put 5 pounds of force on the table. So the same amount of force. But now the question is, which one puts more pressure on the surface? And the one that touches in a smaller area. So pressure is going to be defined as, 3 little lines means defined, as how much force there is per area. So pressure is force divided by area. And there's a demonstration I like doing with my students, but it involves a large wooden ball and a smaller steel ball. In order for this demo to work, you really have to carefully find wood and steel balls that have the right size to make this work. But here's what you do. You put the wood ball in one hand and the steel ball in the other hand and ask the students which one weighs more. And it turns out that the wood ball actually weighs more if you choose the balls correctly, size and density and that. But if you have a wood ball that weighs more than the steel ball, it puts more force on your hand. But because the steel ball is more dense, even though it puts less force on your hand than the wood ball, the force that it does apply is over a much smaller area, and students will feel a greater pressure on their hand from the steel ball, even though they're feeling more force from the wood ball. And they're very surprised. Students think that it's a trick and that they must have the same force. So the thing I need you to understand is that force is not the same thing as pressure. People who aren't careful will often use the word force when they mean pressure and vice versa. So we really want to make sure we're choosing the correct word here, because if I ask you which one produces more pressure, that's a totally different question than which one provided more force. Okay, so pressure is force divided by area. And then we can look at the units. Force should be measured in newtons. Area should be measured in square meters. Are these the fundamental units of pressure? Well, they are some units of pressure, but they're not the fundamental. Fundamental means you can't break it down any farther. And newtons, or force, can be broken down into mass and acceleration. So newtons is the same thing as kilogram is mass, meters per second squared is acceleration, and then we're still dividing by the area. So we have a fraction over a fraction, we copy dot flop, and now we have this. So we have a meter is going to cancel out with the square of the meter there. We'll be just left with meters in the bottom. But now these are the fundamental units of pressure. Kilograms per second squared meters. And another word for fundamental is the MKS system. We should measure everything in meters, kilograms, and seconds. Now there is a common unit for pressure, a one-word unit, and that is pascals, named after Blaise Pascal. And so let's go ahead and compare metric units of pressure to imperial units of pressure. So I have a meter stick here, and so this square here would be 1 square meter. And then this is my same meter stick, but I also have inches marked on here, and that would be 1 square inch. You can see 1 square inch is much smaller than 1 square meter. All right, same thing, but just from a different perspective, looking at an angle here. And I have a mass set. The largest one here is 1 kilogram or 1,000 grams, which weighs 9.8 newtons. That's metric, or also weighs 2.2 pounds. That's imperial. So the 500 would weigh 1.1 pounds, 200, 200, 150, 220s, and a 10. So let's take this 500, pull it over here, and 500 grams is 1.1 pounds, but we'll say, hey, that's kind of close to 1 pound. If I had 1 pound concentrated onto 1 square inch, that's 1 pound per square inch, or 1 psi, which stands for pounds per square inch. And if I took this one here, 100 grams, that's 0.98 newtons. That's pretty darn close to 1 newton. So let's take 1 newton and set it here. But we want to take that force of almost 1 newton and distribute it over the 1 square meter. It's like melting it down and rolling it out over that whole thing. That mass here might be rolled out as thin as aluminum foil. So, but if I had 1 newton distributed over 1 square meter, that would be 1 newton per square meter, or 1 pascal. Now we have to compare these two. 1 psi to 1 pascal. This is a whole lot more pressure. 1 psi is a whole lot more pressure than 1 pascal. I could do dimensional analysis and convert pounds into newtons and square inches into square meters. If we do that, we're going to find that 1 pascal is a tiny amount of pressure. And if I get rid of the 3 zeros here, and then get rid of 3 zeros there, or get rid of the 3 zeros makes it 1,000 times bigger, and makes this 1,000 times bigger. Even still, 1 kilopascal is still a small fraction of a psi. So pascals are really a tiny amount of pressure. So small that we often use kilopascals instead of just pascals. So pressure. And if we had an elephant, if you could imagine an elephant rocking back on 1 foot, and a person here in high heels rocking back onto 1 heel, which one is going to put more force on the ground? And if you're not careful and didn't listen to the question was which one put more force on the ground? And that's the elephant. If it weighs 7 tons, it puts 14,000 pounds of force on the ground. The person here, if they weigh 140 pounds, they just put 140 pounds of force on the ground. Okay. The question now here is who puts more, or that was the original question. Now the question is which one puts more pressure on the ground? So we have to know the area. Let's say that that is a circle, 1 foot in diameter, this many square inches. This is a 1/4 inch heel, not a 1/4 inch high, but a 1/4 inch by a 1/4 inch. So this many square inches, this force divided by that area, and this force divided by that area. The elephant did not put very much pressure on the ground, but the person in high heels put a lot of pressure on the ground. All right, let's relate this to the medical field here. And a needle. Would you prefer to have a sharp needle or a dull needle? And that's an easy question. But let's ask this question. If you had a sharp needle or a very blunt, dull needle, which one is going to take more pressure to push that into a vein? And the answer is it's going to take the same amount of pressure. Okay, because it's kind of like having that thumbtack here. The force was the same, but there was more pressure on here. To get a needle into your skin takes a certain concentration of force to part the cells in your skin, and that concentration of force is pressure. Okay, so if you had the sharp needle, it touches your skin in a tiny little area, so you need a tiny amount of force to push it into your skin. The dull needle touches your skin in a larger area, so you need a lot of force to push this into your skin. In fact, the tip here would go into your skin quite easily, but the head there you could get going into your skin if it was like the end of a pipe that you pushed really hard, and boy, that mental image is a little rough. But pressure is the same, it would just take more force when it was dull. All right, another connection to the medical field. This is called a Picc Catheter. And you would insert this into your arm here, and it's going to go down and get actually into your heart. It's so you can put medications directly into your body without having to get stuck by a needle over and over and over. And you can, periodically you need to flush this line with just a saline solution. But if you're a nurse, you know this. Never flush a Picc line with a 3 cc, that's cubic centimeter, same thing as a milliliter. Never flush it with a 3 cc syringe. But I had a hard time saying that. Always use a 10 cc or greater so you don't blow out the line. Now, why would that matter? You get the Picc line here, and you have a whole variety of different syringes you can use. This would be like the 10 cc one, and then a much smaller one. But when you push on the end here with your thumb, you're pushing with some amount of force. That amount of force distributed over a large area is going to be a small amount of pressure in that fluid. But if you push with this one with your thumb with the same amount of force onto a small area here, you can create a lot of pressure. And if there's a blood clot or something in there, it could blow up the line. Not a good idea. It says also right here that you don't want to push more than 5 milliliters per second. So you got to make sure that when you flush this line, you do it slowly so you don't create too much pressure. Snowshoes, do they put less force on the snow or do they put less pressure? Well, if you're not careful, you would say they put less force on the snow, but that's not true. The force they put on the snow is just what you weigh. And when you take your force and you distribute it over a much larger area, less pressure. So how can you, if you're driving into some cabin here and you get stuck in the deep snow, what can you do to effectively put snowshoes on your car? Well, let out the air pressure. Normally there would be about 32 psi of pressure inside the tire, so there'd be about 32 pounds per square inch against the snow. And if you just flatten the tires to, say, 8 psi, that's 1/4 as much pressure, the tire is going to spread out over 4 times as much area, and you'll float much higher onto the snow. At Great Sand Dunes National Park here in Colorado, you can go behind the sand dunes, and it says, point of no return, 4-wheel drive only, soft sand ahead, tire pressure 15 pounds advised. Well, I wish they had gotten their physics right here, at least with their units. That really should have said 15 psi or 15 pounds per square inch. But you're supposed to lower your tire pressure to about half as much so that you won't dig into the sand like this guy did. You really should stop. That's the first rule of holes, is if you're in one, stop digging. But if he had just deflated his tires before he got onto the sand, wouldn't have gotten stuck. These are pretty cool traction devices. You can just unbolt your tire, bolt these things on, and it way increases your area so that you can drive on the snow really well. Okay, so we have some really fat bald tires here, some thin bald tires, fat treaded tires, and thin treaded tires. And which tire is going to grip the road better? Well, let me ask the same question. which tire has more friction on the road? Friction, so we just studied that last time. The force of friction is less than or equal to the coefficient of friction times the normal force. These are the only two variables that affect the force of friction. This is what materials are touching. So if this is rubber on asphalt, and same here, and same here, and same there, and let's say the larger tires don't appreciably change the weight of the car, so when you put this tire on a car, it's really just about the same normal force on each tire. So you really should get about the same amount of friction. Let's see what the wider tires do, or let's see why you would get the same amount of friction from a pressure perspective. So let's say that on one tire here we got 480 pounds, and on this tire we have the same amount of weight on that one tire. And that tire squashes against the ground and then spreads out over, we'll just make it up and say that's 12 square inches. This one touches the ground in 8 square inches. So if I take this much force distributed over this much area, you get 40 pounds of force on each square inch. This much force distributed over that much area would be 60 pounds of force on each square inch. Now let's come back to friction. Let's do it over here. Right here, that little square inch has 40 pounds of force on it. That would be the normal force. If the coefficient of static friction is 0.25, you just take 40 times 0.25 and you would get 10 pounds of force here, and same for everything else. We'll do the same thing over here. If I have 60 pounds of force on that 1 square inch, that's the normal force on that 1 square inch, multiplied by the coefficient of friction, we'd get 15 pounds of friction on that square inch, and 15 here and there and there and there and there and there. Add up all the little friction you get on each little square inch, and we would get 140 pounds of friction total. Do the same thing here. There's more friction on a square inch, but there are fewer square inches, and you get the same amount of friction. Okay, so why do we have treads on tires? Well, that's to make sure that the materials that are touching each other are the same. We want the rubber to actually touch the road. So if there's standing water on the road, the tread will displace the tire, displace the water, and better allow the rubber to actually touch the road. So race cars use treaded tires when the road is wet, but they use bald tires when the road is dry. Well, if it doesn't matter, if you get the same amount of friction, why would you have two sets of tires? Well, it comes back to this problem here. A bald tire would actually touch the ground in more area than the same tire with chunks of it missing where the tread is. But this tire here has more friction in a given square inch, so that tire is going to wear out quicker, and you'd have to change your tires more often. So the race cars use bald tires not to get better grip, but just to allow the tires to last longer so you don't have to change them out as much. Finally, I want to just look at bed of nails. Typically when you see bed of nails, it's with some ninja guy or some real macho person that just blocks the pain out of their mind. But it really is just a physics thing. Now this is actually a bed of nails I have in my classroom, and this one I use only for myself. It has 2,000 nails in it, and it's taken me quite a while to work up to 2,000 nails. I have a bed of nails I let my students use, and it just has like 4 or 5. You got to start 4 or 5 nails. You got to start small and work your way up. Good idea? Bad idea. Let's see it this way. Let's say that there's one nail sticking out of a piece of wood and you step on it with your shoe. That one nail can go right through your shoe. I'm saying this is a 100-pound person just to keep the numbers easy, but if I have 100 pounds on one nail, that's just 100 pounds per nail. Okay? But if I had 2 nails, well, that's 100 pounds on the 2 nails. That's half as much pressure per nail. 5 nails, 100 pounds per 5 nails, that's only 20 pounds per nail. 10 nails, okay, only 10 pounds per nail. And I think if you put your foot on that, your foot would not go through that, because that's not enough to go through the rubber. It might hurt if you step with a bare foot, but probably not going to go through the rubber sole of your shoe. So this bed of nails has 2,000 nails on it, and you might only be able to get your body touching 1,000 nails, but 100 pounds of your force evenly distributed over 1,000 nails is only 0.1 pounds of force per nail. It's just like you just took your finger and just lightly pressed the one nail. It is not very much force. That's pressure. That's all I have to say about that. Force divided by area, but make sure you're knowing the difference between force and pressure and using the right word in the right context.